All right, let's pull back the curtain on something you use every single second, but probably never think about. We're talking about the invisible gatekeepers inside your phone, your laptop, pretty much all modern electronics. These are the tiny, unsung heroes that make our digital world even possible.
Seriously, just think about it for a second. Right now, all around you, there's Wi-Fi, Bluetooth, 4G, 5G, radio stations, a whole storm of signals. So how in the world does your phone lock onto just one of them for a call or a video stream and just treat all the others like they don't exist?
Well, the answer is this microscopic little component that was created to solve what seemed, for the longest time, like a totally impossible engineering problem. It's an incredible story of ingenuity, and it all starts with this mission to control frequencies.
So to get our heads around this, we need to talk about filters. Now, in electronics, a filter is basically a roofless bouncer at the door of a very exclusive club. Its one and only job is to decide which frequencies get in and which ones get kicked to the curb.
So here's the key idea. A filter is just a circuit that's built to be picky. It creates what's called a passband. That's the range of frequencies it likes, and a stopband for everything else it wants to block. Honestly, without these, communication would just be a chaotic mess of noise.
And, these filters come in a few basic flavors. A low-pass filter lets the low stuff through, think the deep bass in your music. A high-pass does the exact opposite. A bandpass filter is what your car radio is doing. It lets just one specific slice or station get through. And then you've got the band stop, which does the reverse, cutting out a very specific, unwanted frequency.
Now, in a perfect world, a filter would be like a brick wall. It would let its favorite frequencies pass through perfectly, and then bam, instantly drop to zero for everything else. But we don't live in a perfect world. Real circuits just can't do that, and this forces engineers into a really tough choice. And this is where it gets really interesting. You're looking at a classic trade-off. On one side, you've got the Butterworth filter. It's called maximally flat, which just means the signal it passes is perfectly smooth, no distortion. The catch? It has a pretty slow, gentle roll-off. On the other side, you've got the Chebyshev filter. This one gives you a super sharp, fast cutoff, which is awesome for selectivity. But the price you pay is these little bumps, or ripples, in the passband that can kind of distort your signal. So engineers learned how to manage those trade-offs. But there was a much, much bigger problem lurking, a physical barrier that honestly threatened to stop the whole microchip revolution dead in its tracks. And the villain of our story? A little component called the inductor. You see, the basic building block of any classic high-quality filter is something called an LCR resonator. It's just made from three simple things: an inductor, a capacitor, and a resistor. Put them together and they create this natural resonance that's just perfect for filtering. And here it is, the impossible problem. You can shrink down capacitors and resistors and print them onto silicon, no problem. But an inductor? It's literally a physical coil of wire. It works because of a 3D magnetic field. There's just no way to print a tiny, effective coil of wire onto a flat, microscopic silicon chip. This was a massive, massive roadblock. So, what do you do if you can't build it? You fake it. Engineers came up with this unbelievably clever workaround. The thinking was, if you can't build a real inductor, maybe you can simulate one using the parts you can put on a chip. And this is the solution, known as the attenuation circuit. It's just brilliant. You take two operational amplifiers, or op-amps, add a couple of resistors and one capacitor, and you wire them up in this very specific way. And the result? The circuit behaves, mathematically, exactly like a perfect inductor. Problem solved. All of a sudden, we could build high-quality filters right on the chip.
But you know how this goes. The story doesn't end there. As technology kept getting smaller and smaller, following Moore's law, a whole new problem popped up. Even the tiny components in that virtual inductor circuit started to become too big for modern microchips. And the new weak link was the resistors. On a modern chip where everything is measured in nanometers, even a tiny resistor takes up a huge amount of precious space. On top of that, it's really hard to make them precise, so a new, even more magical solution was needed. And that solution is the switched capacitor filter. And folks, this is pure genius. Engineers realize something. Making precise resistors on a chip is hard, but making precise capacitors is easy. So they took a tiny capacitor and two little switches controlled by a clock. By flicking those switches back and forth incredibly fast, they could make the capacitor shuttle a tiny bit of charge, perfectly mimicking the behavior of a resistor.
And here is the absolute best part. The value of this virtual resistor isn't set by some physical thing. It's set by the frequency of the clock. You want a different resistance? No problem. Just change the clock speed. This gave engineers a tiny, perfectly precise and digitally tunable filter that could be plopped onto any chip. It's incredible.
So let's just recap this incredible journey. Filters are the gatekeepers that make our electronic world work. The biggest challenge was getting that bulky inductor to fit on a microchip. The first brilliant hack was to create a virtual inductor with op-amps. But the ultimate solution, the one that's inside the phone in your pocket right now, uses a clock and a tiny capacitor to create the perfect, tunable, microscopic filter.
I really hope you enjoyed that deep dive into the hidden world of electronic filters. If you found this stuff as cool as I do me a favor and hit that like button. Subscribe to the channel and definitely ring that notification bell so you don't miss our next explainer.
It really makes you wonder, doesn't it? What other impossible components born from equally brilliant solutions are hiding in plain sight inside the devices we use every single day? Thanks so much for watching.